Hi statisticians, and welcome to section 7.6. So this is the last section in chapter 7, which remember is all about normal distributions. So the distribution that has this kind of a shape. And we've talked about a lot of properties now of normal distributions. And one of the most important properties was one that we went over in the section 7.5 notes called the central limit theorem, which basically said as long as your sample size is large enough, which in our case is greater than or equal to 30, that the distribution of sample means approaches normal. So that's really helpful for us because we like normal distributions. We've got that z table, so we can use normal distributions to do a lot of things that we can't just do with any old distribution. So we'll finish off this chapter by talking about the other distribution that we've become familiar with in this course, which is the binomial distribution. So remember, a binomial probability or a binomial trial is where you only have, let's see, I'll just give you a little recap here. So there's only two outcomes. There's only two possible outcomes, and we call them success or failure, but that's not necessarily, they don't have to necessarily have like a good or a bad connotation. Basically, it's just important that there are two outcomes. All the trials are identical, so nothing changes between trials. And then we say P is the probability of success, and we say Q is the probability of failure. So basically Q is everything that's left over after P. Okay, so recalling that, let's start our warm-up. The probability that a new vaccine will protect adults from cholera is known to be 0.85. The vaccine is administered to 300 adults who must enter an area where the disease is prevalent. We would like to know the probability that more than 280 of these adults will be protected from cholera by the vaccine. So the hint says this is a binomial experiment, and we're going to use those formulas for the mean and the standard deviation of a binomial experiment to find the mean and standard deviation for this particular example. And really, that's all it's asking us to do for this particular problem. So looking at this, let's talk first about why it's clear that this is a binomial experiment. So first of all, there's 300 adults. They're getting this vaccine. Now, the vaccine either protects them from cholera or it doesn't. So basically, like they either get cholera or they don't. So P is the probability that it keeps an adult from getting cholera. Probability of success is 0.85. Now that tells us that the probability that this vaccine does not protect an adult from cholera is whatever's left over. In this case, 1 minus 0.85 is 0.15. So 85% probability and 15% probability. Okay, so we know N and we know P, we know Q. The last thing that we need to know in the formula is N, which is the number of trials. And in this case, because the vaccine is administered to 300 adults, that is our sample size. So N is 300. And I'm just going to use those three values in these two formulas to find the mean and the standard deviation for this binomial distribution. So I'll start with the mean. Mu is 300. Oops, sorry, let me write out the formula. Mu is N times P. Well, in our case, N, the sample size, is 300. And P, the probability of success, is 0.85. And so when I throw those into my calculator, that actually comes out really nicely. The mean, or the expected value, is 255. Now, the standard deviation has also a really friendly formula, the square root of n times p times q. So in this case, again, n is 300, p is 0.85, and q is 0.15. And so when I throw those into my calculator, I'm going to round this to 2 decimal places, and the standard deviation is approximately 6.18. Okay, so that's all we're going to do on this particular example, but that should give you a little bit of a refresher on binomial distributions and binomial trials. Okay, so now let's talk about what binomial distributions look like. Consider binomial distributions for which the probability of success, p, is 0.25, the probability of failure is 0.75, and the number of trials is n. And what we're going to do on this page and the next page is just like look at different graphs for different values of n, so different numbers of trials. The graph on the left below is n equals 3. So right here, n equals 3. Now, when you have 3 trials, there are actually 4 things that can happen. It's always one greater than your number of trials. You could have 0 successes, you could have 1 success, 2 successes, or 3 successes. And the reason that it's always one more than the number of trials is because you'll have 1 up to however many trials you have, 1, 2, 3 in this case, but you also have 0. So because of this 0, we have to add 1 to the number of trials, and that's how many bars we would have. Okay, so when I look at the shape of this distribution, it doesn't really look terribly, I don't know, it doesn't look terribly familiar. But it's also a really, really small number of trials. So let's see if we can get something a little bit better by increasing the number of trials. When the number of trials is 10, well, now the shape might start to look a little bit more familiar to you. This looks a little bit more normal. Now, I wouldn't say it's perfectly normal, but it definitely has a normal-ish shape, meaning that it's symmetric, mostly, looks mostly symmetric. It's got kind of the highest point in the middle, and then it trails off on both sides. Now, if we flip to the next page, again, we're increasing the number of trials. So now on this third graph, the number of trials is 25. And so you'll notice this should look a little bit more normal to you. And then last graph on here, n equals 50. And that also looks like it's really trending toward a normal shape. So I think what we can probably conclude from this is kind of much like we saw in the previous section. The larger value of n, the larger the value of n, in our case, the larger the number of trials, the more normal, and by normal I mean like that bell curve shape, the more normal the distribution. As n gets larger and larger, our number of trials gets larger and larger and larger, the distribution of the binomial experiment gets more and more normal. Now, this is really good news because, again, we like normal distributions. We have a table that goes with them. We can do all kinds of really friendly things with normal distributions that would take a whole lot more work if our distribution was really anything other than normal. Now, before we continue, let me just point out on all of these little side lists of numbers, we're given the mean, and we're also given the standard deviation for each of these situations. Now, In all of them, P and Q are still 25 and 75%, but remember the N changes, and there's an N in both of those formulas. So even though the P and Q are the same, from N equals 25 to N equals 50, that is going to change the mean, and it is going to change the standard deviation. But we're given those values in all of those graphs. So we have those, and we're going to use them in just a couple minutes. So let's look at an example of this. The owner of a new apartment building must install 25 water heaters. From past experience in other apartment buildings, she knows that Quick Hot is a good brand. A Quick Hot water heater is guaranteed for 5 years only, but from the owner's past experience, she knows that the probability that it will last 10 years is 0.25, 25%. Coincidentally, that's the same probability as all these graphs that we have, so that's helpful. Here's our probability of success. What is the probability that 8 or more of the 25 water heaters will last 10 years? Define success in this case to mean that a water heater lasts 10 years. And note, and we will come back to this little note later, the probability that we have 8 or more successes, remember R is the number of successes. So probability that the number of successes is greater than or equal to 8 is approximately equal to the probability that X is greater than or equal to 7.5. I'll say more on that later. So how would we find the probability that X is greater than or equal to 7.5? Well, this is exactly the same problem that basically we've been getting for the last several sections. I give you an X. Well, you don't really want to deal with X. You want to convert this to Z. And remember, the formula for converting this to Z is Z equals X minus mu over sigma. It's one of our most commonly used formulas in this entire class, and we use it all through chapter 7. So if you haven't committed it to memory, you should. It is in your formula packet, but we just use it so much. Okay, so I'm going to take this 7.5 and I'm going to plug it into this formula and convert to Z. So the other question is, I'll do it right here. The other question is, do we have mu and do we have sigma? Because I need to plug those into the formula. So let's look back through the numbers in this problem. The owner of a new apartment must install 25 water heaters. Well, in the language of the problem, or in the language of binomial trials, this is our sample size. This is the number of trials, 25 water heaters. Here is our probability of success, 25%, which would tell us that our probability of failure is going to be 1 minus that, which is 0.75. Okay, so here's all of our values. N equals 25, P equals 0.25, and Q equals 75. Now, we could find mu and sigma. I mean, remember, in binomial land, these have very friendly formulas. So you could absolutely find those like so, but also actually this is exactly modeled right over here. 25 trials, probability of success is 25%, probability of failure is 75%. So even though they're both very easy to do, we actually already have them. 6.25 for mu and 2.17 for sigma. So I'm just going to shortcut this and use those. Everywhere I see a mu, I'm going to put 6.25. There's the mean. And everywhere I see a sigma, I'll put 2.17, which tells me that when I convert this thing to Z, let's see, throwing that in my calculator, this problem is going to become X turns into Z, 7.5 turns into, I'm getting 0.58. So probability that X is greater than or equal to 7.5, converted over, is the same as the probability that z is greater than or equal to 0.58. Okay, so now I'm going to pull out my z table that is in your formula packet, or also I think it's in 7.3 notes. So 0.5 and then scroll over to 8, and I find that the probability associated with 0.58 is 0.7190. But hold on one second, because 0.7190, this is left area. Remember, in the table, it always gives you the left areas, which would look like this. Z is to the left, Z is less than. But our problem doesn't say less than or equal to, it says greater than or equal to. So the one last thing that I need to do is just adjust this by subtracting it from 1, and that's going to find the right area. So 1 minus 0.7190, which is 0.2810. Okay, so that's the probability that 8 or more of these water heaters will last 10 years. Okay, so let's go back to one really important part in this problem, and that is this little step right here. The problem asks us, what is the probability of 8 or more successes? But we actually found the probability of 7.5 or more successes, kind of. We found the probability that x is greater than or equal to 7.5. So let's think about why that is. And to do that, we're going to look back up at this distribution that we used to find the mean and the standard deviation. So you'll notice that 7.5, it's actually marked on here for you. I'm sorry, let me go back again. We want to find 8 or more. Well, 8 or more is here and forward. But you'll notice that this 8 is right in the middle of a bar. Remember how we do this when we're making histograms? We kind of fluff up the bars on either side so that they all kind of run flush to each other. Like the 5 is in the middle of the bar, and then we fluff that up. So these bars actually go from a 0.5 value, like this one is 1.5, this value is 2.5, here's 3.5, and so on. So 8 is right in the middle of a bar, and what we really can't do is start an area right in the middle of a bar. So because we wanted to find the probability that our successes were greater than or equal to 8, that tells me that I want to find basically the area of the, let's see, how do I say it? The 8 bar, meaning this area. I want to find this entire area, plus all of these bars after it. The 10, the 12, all of those. Okay, so the area of the 8 bar plus the area of the 9 bar, the bar above 9 right here, the 10 bar, the 11, the 12, the 13. They start getting smaller and smaller at this point, but still we want to add up all their areas. I want to find the area of that entire bar above 8. Well, the entire bar above 8 starts at 7.5. So even though I'm asking for the bar above 8, 8 and above, I start my probability here. I start my random variable at 7.5. So that's why we're making that adjustment. And this actually has a name. This is something called a continuity correction. Basically means I'm making an adjustment because this is a bar graph and I can't start in the middle of a bar. So that's what this is talking about. Can't start in the middle of a bar. Can't start in the middle of a bar on a bar graph. So I want to talk about this actually a little bit differently than how I have it on the notes. So let me focus on this for just a few minutes. Don't focus so much on this little part. Let's talk about this. The probability that R is between 6 and 10. Now notice, actually one of the most important things that's on here is this or equal to, and this or equal to. So this would mean I want to include the 6 bar, the 7 bar, the 8 bar, the 9 bar, and the 10 bar. And when I'm saying bars, I mean on a bar graph. So I'm just going to scroll down a little bit. I have a nifty ability to be able to give myself more space at the bottom of a page, but you can maybe, I don't think you have a back page. I don't know. Just do this off in the margin or something. It doesn't have to be big. So let me draw a quick bar graph that would represent this scenario. Now, I don't know how far out this goes, but I do know that there's going to be a bar above 6, a bar above 7, a bar above 8, and I don't really know what the heights are. A bar above 9, and we'll do this, a bar above 10, like this. Now, who knows what's on this side? Who knows what's on this side? I don't really care. I know that in this particular example, it's asking me to find the areas of all the bars from 6 to 10. And this means that I want to include the bar at 6, right? And then less than or equal to 10, so I want to include the bar above 10. Okay, so let's look at what this really means. If I want to find all of these areas, well, if I want to include the bar above 6, I can't actually start right here at 6. I can't start in the middle of a bar. Well, the bar above 6 actually starts at 5.5. That's how I get this bar above 6. And actually, the bar above 10, well, here's 10 right in the middle of it. The bar above 10 stops at 10.5. So if I want to include all of these bars, everything from 6, 7, 8, 9, and 10, I need to start finding the area at 5.5, and I need to stop finding the area at 10.5. So, using this continuity correction, the probability that the number of successes is between 6 and 10 is actually equal to the probability that x is between 5.5 and 10.5, because this is where the bars would actually start and end. Okay, I want to focus on this a little bit more, so I'm actually going to just do a couple more examples here. Let's do, how about now I said the probability that the number of successes is between, I'm going to stick with these same numbers. The probability of that the successes is between 7 and 7 and 9. Again, I need to look at these symbols really closely. When it says R is greater than or equal to 7, or 7 is less than or equal to R, what this is telling me is I want to include this bar above 7. I want to include this, which means that I actually want to start at 6.5, because that's where this bar starts. And I want to include the bar at 9, which actually ends at 9.5. Okay, so the probability that R is between 7 and 9 is the same as the probability that x being a random variable, is between 6.5 and 9.5. Okay, let's do another one. Almost the same problem, but now just a smidge different. I'm going to say the probability that our successes are between 6 and 10 again, but notice now there's a big difference between this example we did earlier, less than or equal to, less than or equal to, and my new example where now I'm saying I don't want to include. Don't include that bar above 6. I don't want to include this bar. I want to start here. And I also don't want to include the 10 bar. I want it to go all the way up to it, but not actually equal the bar above 10. So I'm going to stop here. Starting here, stopping here. And this middle bar is included also. I just didn't write it. Okay, so this one would equal the probability that my x value, my random variable, starts at 6.5 and ends at 9.5. So this is interesting because notice these probabilities are the same, and it really all comes down to this symbol. It's like, do you want to include the bar or do you not want to include the bar? Because if I don't want to include the bar above 10, then that really means that I'm stopping right at the end of the 9 bar. All right, so one more just to really emphasize this. Let's do probability that the number of successes is between, let's see, 6, and we're going to do inclusive, so less than or equal to on 6, and 8 exclusive. So number of successes is between 6 and 8, but it could equal 6. I do not want it to include 8. All right, so let's mark this on here. I've really made quite a mess of my picture here, but I want to include the bar above 6. It says or equal to. So that's how I know it could equal the bar above 6. So this one's included. The bar above 8 is not included. So do not include this bar. Only include everything up to that bar, which would mean that my x values are going to start at 5.5, which is that left side of the 6 bar, and it's going to stop at 7.5, which is just on the left border of the 8 bar. So it's really all about this symbol. And this is called continuity correction. It's basically turning a bar graph into like a continuous probability. Okay, so you'll have to do that just a couple times on the homework, but just be aware that this is a process that happens when you're in a binomial setting. Also note, this one's really important. In order to use a normal approximation for a binomial trial, which is of course what we want to do, both NP and NQ must be greater than 5. That has to happen in order for us to be able to approximate a binomial trial using, or a binomial distribution using a normal distribution. NP and NQ must both be bigger than 5. Okay, so last thing that we need to do is talk about the sampling distributions for proportions. Now, we've kind of done this in the setting of sample means. We've talked about in section 7.5 the sampling distribution for the mean, so that's when we did distributions for x bar, and that's where we talked about the central limit theorem. So now let's basically do the same thing in a binomial setting, and these things are called proportions. So suppose we repeat a binomial experiment with n trials again and again and again. and we basically record the number of successes over the total number of trials. Total number of trials. Well, that would give us like almost like a sample probability. And that's kind of what this is. First of all, we read this p hat. It has a little caret on the top. P hat is like our sample probability. So sample probability, or p hat, our sample proportion, is like no one gives you a probability in the problem, but they say, hey, this thing happened 5 out of 10 times. Well, then you would kind of guess that the probability is 5 out of 10 or 1/2. So you're just kind of estimating a probability based on the problem. That's just an example. Okay, the fact is, if NP and NQ are greater than 5, that is a really important criterion that always has to be met, then the random variable p hat can be approximated by any random variable x with the mean equals p, probability of success, and the standard deviation equals the square root of pq over n. So that's nice. Now we have a formula for the mean and the standard deviation, and honestly, they're really friendly formulas. So let's put this to work. The annual crime rate in the Capitol Hill neighborhood of Denver is 111 victims per 1,000 residents. That means that 111 out of 1,000 residents have been the victim of at least one crime, and these crimes range from relatively minor to major crimes. Suppose that we study 50 residents as a binomial trial. The random variable r, which takes values from 0 to 50, represents the number of victims of at least one crime in the next year. What is the probability p that a resident in the Capitol Hill neighborhood will be the victim of a crime next year? And what is the probability q that a resident will not be a victim? Okay, well, we're given the fact that 111 out of 1,000 residents have been the victim of at least one crime. So that would tell us that the probability of a resident being the victim of a crime is 111 over 1,000. And you can either throw this into your calculator, or maybe you don't even have to because it's a very friendly denominator. That comes out to 0.111 as a decimal. And then the probability q that doesn't happen, a resident will not be a victim, is just 1 minus that value that we got for p, so 0.889. Okay, so there's our p and q, and let's continue this on the next page. Consider the random variable p hat equals r over n. Can we approximate this distribution with a normal distribution and explain why or why not? Okay, well, remember the criterion for being able to approximate using a normal distribution is that both NP and NQ must both be greater than 5. So that's what we need to check. Are both NP and NQ greater than 5? Now in this particular problem, we are given that n equals 50. So there's our n. We also found p equals 0.111 and q equals 0.889. So we've got n, we've got p, and we've got q. So we'll use that here just to check. Let's first check NP. NP equals, n is 50, p is 0.111, and so when I throw that into my calculator, I find 5.55, which is greater than 5. So that test is passed. And then the second thing we need to do is check that NQ is also greater than 5. So NQ, well, n is 50. Q is 0.889. And so For that, I get 44.45, which is certainly greater than 5. And so we've passed our second test. So can we approximate the distribution with a normal distribution? Yes, because NP and NQ both are greater than 5. So since we can approximate P hat using a normal distribution, let's lastly find the mean for this particular distribution. So mu sub P hat and sigma, the standard deviation for this distribution. So sigma sub P hat. Now remember, we have very friendly formulas for these. They're on your previous page. The mean is just P, and sigma is just the square root of PQ over N. Okay, well, this is just P, and we know that P is 0.111. So there's the mean of this distribution, mu sub P hat. And the standard deviation is PQ over N under the square root. So in our case, well, everywhere we see a P, we'll put 0.111. Everywhere we see a Q, 0.889. And everywhere we see an N, 50. And when I throw that into my calculator, I'm going to round to 3 decimal places, 0.044. So there's the mean and the standard deviation. Now we will go over the I really understand this problems on this page. You should pause it and try, it's just this one problem. So pause it and try this, and then after we go over this, we'll talk a little bit about the upcoming test. So hopefully you've had a chance to try this problem. It says, for many years of observation, a biologist knows that the probability is only 0.65 that any given Arctic tern will survive the migration from its summer nesting area to its winter feeding grounds. This is a type of bird. A random sample of 500 of these birds were banded at their summer nesting area. Use the normal approximation to the binomial and following steps to find the probability that between 310 and 340 of these banded Arctic terns will survive the migration. Let R be the number of surviving terns. First of all, find mu and sigma for the given distribution. Okay, so going back to the beginning of the notes, remember that for a binomial distribution, mu equals NP and sigma equals square root of NPQ. This is just for any binomial problem. Okay, so we'll use those here. Mu equals NP and sigma equals the square root of NPQ. Well, now we need to get all those numbers from this problem. So a biologist knows that the probability is 0.65 that any Arctic tern will survive, which we're considering that to be success. So here is our probability of success. P equals 0.65. A sample of 500 terns were banded, so N equals 500. There's our N. And then use the normal approximation, okay, blah, blah, blah. Now, that's all we need. So P equals 0.65, N equals 500, and then last thing, Q, well, if P is 0.65, then we just subtract that from 1, and Q is 0.35. So we've got all of our values, and we'll plug those back in. Mu equals NP. Well, everywhere I see an N, I'm going to put 500. Everywhere I see a P, I'll put 0.65. So 0.65 times 500 is 325. So there's my mean for this distribution. Now, square root of NPQ. So everywhere I see an N, 500. Everywhere I see a P, 0.65. And everywhere I see a Q, 0.35. And I'll round this to 2 decimal places, 10.67. Now, this next part is asking me to use a continuity correction. So I'm just going to think about what this distribution looks like. This is basically saying include the bar above 310. Well, the bar above 310, who knows what it looks like, but here's the bar above 310. Well, the bar above 310 actually starts 1/2 step down from that. It starts at 309.5. So 309.5. And now I'll turn this into x. X is a random variable. And I want to include, again, I want to include the bar above 340. So some stuff is going to happen here. I'm not going to draw all those bars, but here is, that's a really big one, don't know why, the bar above 340. Well, I want to include this entire bar, which means I need to count it all the way to the end, which is 340.5. That's where this bar ends, 340.5. So this is the probability that I actually want to find. Okay, so that carries this down here. Convert the condition 309.5 is less than or equal to x is less than or equal to 340.5 to a condition in standard units. When someone says standard units, that means z. Convert these x's to z-scores. Okay, so I'll do that using our favorite formula, z equals x minus mu over sigma. So again, it's nice because in part A, we found mu and sigma. So we have those values. So I will throw the first one in here, 309.5. Everywhere I see an x, minus, everywhere I see a mu, I'll put 325 over sigma, 10.67. And when I do that, I'll round to 2 decimal places, negative 1.45. Okay, so there's my first z value. Now on the second one, I'll do the same thing. Z equals, everywhere I see an x, now I'll put 340.5 minus 325 over 10.67. And when I throw this into my calculator, I find 1.45. So that tells me if I want to find the probability that the number of successes, R, is between 310 and 340. This is actually kind of like a 3-step process. The probability that R is between 310 and 340 is the same as, now I need to use a continuity correction because of those bars. I've already done this part. It's the same as saying the probability that x is between 309.5 and 340.5. But then again, I'm going to change this around because I don't want to deal with x's. I want to deal with z's. It's the same as the probability that z now is between negative 1.45 and 1.45. Okay, so really all I have to do, all I have to do is find these areas from my table, my z table, and then subtract larger area from larger area minus the smaller area. Okay, so I'm looking at my table and I'm first going to look at this value on my z table because that's the bigger area. So 1.4, scroll, 5. On my table, let's see, I'm looking at 0.9265. That's the larger area. That's the area for z equals 1.45. Now I'm going to flip to the other side where I have the negative z scores and find negative 1.45, 0.07 0.835. Okay, now I'll throw those into my calculator, and when I do, 0.8530. So that is the probability that somewhere between 310 and 340 of these total of 500 turns will survive. Okay, so I hope all that makes sense. This is the end of chapter 7, which means now you are going to need to take exam number 4. So all the other exams have included 2 chapters. And that was because the other chapters were a little bit shorter, actually significantly shorter than this one. This one is 6 total sections, so this is going to be just a good chapter to stop and just take an exam on only chapter 7. So a couple things here. First of all, exam 4 only covers all of chapter 7. Now, exam 4 must be taken on April 7th, which I believe is a Tuesday. So you can take it any time on Tuesday. It will open up at actually at midnight. So I don't know if you want to take it at 2 in the morning on Tuesday, up to you. It has to be finished by midnight. So you have all day Tuesday to take it, but you do have to finish it on April 7th. Now, your time limit for this test is going to be 75 minutes. It'll be automatically timed on WebAssign. I'll say that. This is all going to be done on WebAssign. It'll be automatically timed. You'll see a little timer ticking down the whole time, kind of like you do, I can't remember if quizzes are timed or not for us. You'll see a timer ticking down the whole time. It will automatically be timed 75 minutes, just like it would be in class. So that's important because don't start it at like 11:30 p.m. because it will close at midnight. So make sure you give yourself enough time so that you have 75 minutes before it closes actually at 11:59 p.m. on April 7th. So don't start it too late at night. A lockdown browser is required, and I sent this out in an email. I sent you a link to be able to download a lockdown browser. Please download this early and make sure that you can use it. Don't wait until like 10 p.m. on Tuesday and then find out that something went wrong downloading the lockdown browser. The exam must be taken on April 7th. So it is completely up to you to make sure that this works ahead of time. All the homework requirements are still in place. So before you can open the assignment that's called exam 4, you'll have to open the exam 4 ticket. This is in your list of assignments right now. And this is basically the same exam ticket that you would submit in class. So you'll just say, I certify that I've earned a score of 70% or above, and you'll just check all of these things on WebAssign. All of these must be done, and you'll submit for testing. Once you've done all of this, then you'll be able to open exam 4. This is basically a prerequisite assignment for exam 4, so if you have not submitted the exam 4 ticket, you can't open the assignment called exam 4. So you have to have this done. Have to have 70% or above. Okay, so the exam is pretty much the same layout as an exam that you would take in class. So you'll start with some multiple choice problems. These are actually all given separately on the test, so I'll say this is actually problems 1 through 5 on the test. It says that it's multiple choice. And then you'll have problems, let's see, 6, 7, 8, and 9 and 10. These are kind of like a 2-part problem. All of these are about normal distributions. So it's just all covering chapter 7. I can tell you number 10 is about some binomial stuff, but everything that we've covered in chapter 7, it will all be on there. Now, you will have to show your work on a lot of the problems. Now, multiple choice problems, there's no work required, and so you won't see anything that looks like this. There won't be a place to type your work. There won't be a place that says upload a file of your work. Multiple choice problems, you don't have to show me any work, but everything else, you'll see a little window that looks like this. Now, you can type your work here if you want. You could upload a file here, and I don't care which one you do. So you're welcome to type what you're doing, just be as detailed as possible. Basically anything that you would show me on the test, you'll just type it out here. Or you can do your work on scratch paper, which you should absolutely do anyway. You should definitely have some scratch paper available, and then you can upload a photo of your scratch work here. So if you want, you can just like snap a photo with your cell phone or with like your camera on your computer. I don't care. Whatever you want to do here. And then upload a file. Okay, so you will still have to show your work here. So hopefully that's clear. The other thing that I want to talk about, actually two more things. This one's really important. Your grade will not be accurate when you finish the exam. In fact, it will be much higher potentially than your real grade. So WebAssign automatically gives 100% for your work. Okay, so that's not great because I'm going to go back and look through all of your work, so that might change. I wish they didn't automatically give 100%. It sort of inflates your grade. So whatever grade you get when you're done, that potentially could change if you lose any points for not showing all of the details of your work. So just be aware of that. The other thing is you have multiple attempts on questions, but each attempt decreases your total score. So let's say there's a question, and I don't know, let's make it easy. So let's say the question is 3 plus 5, and here's your little answer box. Now, if on the first answer you enter 8 and it says that that's correct, well then you'll score 100% done on that problem. So, okay, that makes sense. If on the first answer you enter 7, then it will tell you, no, that's not correct. You can still answer again, so you'll get a second attempt to answer this exact same question, and now you answer 8, and it will say yes, but on this attempt, because it took you 2 attempts to get there, you'll get 80%. So from here to here, there's a 20% decrease. And then if you did it a third time, so let's say on your first one, you entered 7. On your second one, you entered 6, and it's still wrong. And now on your third attempt, you finally get to 8, and it's correct. Now you'll get 60% on the problem. So it is imperative that you try to get the right answer on the first time. You can have 3 attempts on the questions, but if it takes you till your third attempt, it's going to automatically dock your score 20% twice. And remember, that's also without any of the work stuff. So make sure that you're doing your best on the first time. Now, the last thing that I'll say about this is obviously you can have your notes and your formula sheet in front of you, but remember, this test is timed at 75 minutes. So there's not a lot of time, not a lot of time for a couple things. There's not a lot of time for checking your notes. And there's also not a lot of time to submit multiple answers. So yes, you can have 3 attempts on every problem, but it all counts in your 75 minutes. If you keep an incorrect answer and you submit your work, I will still grade it. Like, you can still get a whole lot of partial credit, just like you could get on an actual test. So what you may want to do is go through the entire test once and then go back to any of those problems that you got wrong and try to submit them. Try to correct them, I should say, because that way you're not eating into that 75 minutes going over one problem for 20 minutes of time, and then you completely miss the last problem on the test because you didn't even get to it. This is just my suggestion, but just keep in mind you are still managing your time for those 75 minutes. If you have any questions about this, please don't hesitate to email me. All of your homework must be done before you take the test, and that test will be available on April 7th. It's not even in your list of assignments now, but April 7th at 12:01 a.m. You will see this in your list of assignments, and it will be available until 11:59 p.m. You can take it anytime that day, but it has to be done. You'll have 75 minutes open to close, and then it has to be all submitted. All your work, everything has to be submitted within that 75 minutes. Good luck.